When I first wondered about how Einstein discovered relativity, I came across his famous thought experiment. The one where Einstein imagined himself moving at the speed of light and switching on his flashlight and wondering, would he see light to be at rest? And somehow this led him to the theory of relativity. And at first I was like, wow, what a mind-boggling experiment. But then I thought, wait a second. What's the problem if you see light to be at rest? I mean, if I travel at the speed of sound and planes can do that, then I see sound to be at rest. And if I swim at the speed of water waves, and ducks can do that, then I would see water waves to be at rest. We don't have a problem there, so what's the problem with light? That's where I realized that there was something deeper going on over there, and I had to connect a few more dots, but finally once I did it, then my mind was truly blown. And therefore, the goal of this video is not just to understand relativity, but to actually do a series of thought experiments, all the necessary thought experiments to truly understand how we discovered relativity. And so if you show some patience and follow along, by the end of this video, you would have a much deeper understanding of what went on in Einstein's brain. And so if you're ready for this, let's begin. So where do we start? Well, let's ask Einstein. Einstein, where do we start? Einstein gives us an overview and says that if we combine our ideas of inertia and Newtonian relativity, the relativity that we already knew about, with electromagnetic waves, then there's only one logical conclusion: special relativity. And that's what we need to understand. And therefore, we need to start with the basics, understand some consequences of inertia and Newtonian relativity. So here's Einstein in an open car coming towards me. But Einstein says, hey Mahesh, that's your point of view. From my perspective, my car is at rest and you and the road are moving towards me. And I tell Einstein, well, yeah, but that's an illusion. You see, it's your car that's really moving, but since you are also moving along with your car at the same speed, you get an illusion that you are at rest. But in reality, you and your car is moving. And Einstein says, well, Mahesh, I can say the same thing about you. Your ground is really moving. And since you are also traveling at the same speed along with the ground, you are the one that gets the illusion that you are at rest, but in reality, you are moving. So how do we solve this? It sounds silly, but how do we solve for this? Well, Einstein says we need to identify an experiment that he can do that will confirm that indeed it is him that is moving. And I say, well, very simple. Einstein, your car is shaking. And if you're traveling on Indian roads, you know you're moving. And Einstein says for the rest of the video, Mahesh, will only consider very special cases where things are going at constant velocity. No shaking, no accelerations whatsoever. And I ask Einstein, but why? Because Einstein says, this is a video on special theory of relativity. Wait, is that where the word special comes from? That's right. The word special comes from the fact that Einstein, when he was initially thinking about it, he only worried about constant velocity motion. So that's what makes it special. We're only considering special cases where things are moving at constant velocity. Later on, he found a way to extend this argument in general to all kinds of motion. General relativity, okay? All right, so Einstein is coming towards us at constant velocity. How do we confirm that it's him that is moving? What kind of an experiment can we do? Actually quite simple. Einstein, take a ball, throw it up. See, what I'm thinking is if he throws up a ball, then because his car is moving forward, that ball is gonna fall behind him. And so from his perspective, it will feel like the ball went back. And we're ignoring wind over here. So if you were at rest, the ball wouldn't go back. And that's how we would know that Einstein is moving. So Einstein, let's do that experiment. So he does that experiment and it doesn't work. The ball comes back to his hand. Why did that happen? Einstein says we forgot something. See, even before the ball was thrown up, it is in motion. It has a forward velocity. And so when it gets thrown up, it continues to move forward because of inertia. Newton's first law, things at motion have a natural tendency to stay in motion. And therefore, as that ball goes up, look, it continues to go forward, and therefore it'll always be directly above Einstein's hand, and therefore it lands back on Einstein's hand. And so because of inertia, Einstein gets the same result as he would get on a ground, confirming that he's at rest. Okay, Einstein, but I have another experiment. This time, Einstein, imagine you're holding a gun, a toy gun, not a real gun, YouTube. Don't censor this, don't ban this, toy gun with toy bullets, okay? And imagine your car is going at the speed of that bullet. Now what's gonna happen when you shoot that bullet? Well, the bullet comes out at the same speed, and therefore, the bullet and your car will go at the same speed, and you see that bullet frozen from your perspective, and that cannot happen if you were at rest. Therefore, you would know you are in motion. So Einstein says, let's do that experiment. Einstein does that experiment and it doesn't work again. The bullet goes forward. Einstein says, again, I forgot about inertia. See, even before the bullet was shot, that bullet was moving forward at the same speed as the car, so the speed of the bullet. And once the bullet gets shot, it will continue to have that same speed, but once the bullet gets shot, it will have an additional speed due to the gun. So this is due to this inertia, and then this is the additional speed because of which it goes ahead with twice the speed of the bullet, and that's why it goes ahead, and therefore Einstein sees everything to be normal, confirming he is at rest. Okay, how about, and at this point Einstein cuts off and says, Mahesh, in the spirit of time, let me tell you, there is no way you can do any experiment with particles to detect my motion. So Einstein is saying, look, any particle that you think of has inertia. And because of inertia, whatever experiment you do, regardless of how complicated it is, because of this inertia, Einstein will always get the same result as he would get when he's standing on the ground, confirming he's at rest. And therefore, he says we cannot use any particle to detect constant velocity motion. So what do? Well, particles have inertia, but what about waves, Einstein? You see, waves don't have inertia. To give you an example, here we have Einstein standing beside a string. Now, if Einstein makes a wave, that wave goes forward on the string. Now imagine Einstein is running at some speed and he makes the wave again on the string. What will be the speed of the wave this time? Would it change because Einstein was moving? No, the speed of the wave on the string depends on the properties of the string, like how heavy it is, how tight it is, what is the material, and so many other things. It does not depend upon whether the source, Einstein, whether he's at rest or is moving. It doesn't matter. So even here, the wave will travel forward with the same speed. And since Einstein is also moving at the same speed, unlike the bullet, look, Einstein and the wave move together, which means it'll appear frozen for Einstein. So since waves don't have inertia, we can use waves to test it out. So let's do that. So this time, let's imagine Einstein's car is moving at the speed of sound. And Einstein makes some sound, he shouts it, that'll also travel at the speed of sound, because just like with the string, this speed does not depend upon Einstein's motion. And now, for sure, both of these would travel together. So let's have a look at it. And that's exactly what happens. Both of them are traveling together, which means from Einstein's perspective, look, that wave is frozen. He will see sound frozen, but we know sound doesn't get frozen when you're at rest, confirming that Einstein is moving. What do you got to say about that, Einstein? And Einstein says, indeed, that's exactly what happens. But Einstein says, hold on, buddy. That doesn't mean I'm at motion. I'm still at rest. Wait, what? You just saw sound to be frozen. That doesn't happen when you are at rest. Einstein says, allow me to explain. He says, I am at rest, but there is a wind going backwards at the speed of sound. And air is going backwards at the speed of sound, and sound is trying to go forward in that air at the speed of sound forward, but because of the air, it's not able to go, and that's why it's frozen. So the reason the sound is frozen is not because I am moving, Mahesh. He's saying it's because there is a wind that's going backwards. That's what's making it frozen. It's very similar to an escalator that goes up and somebody tries to go down at the same speed. He gets stuck in between, but that doesn't mean I am moving, right? That's a good point. Okay, what if we ignored the air? Well, Einstein says if you ignore the air, there is no sound waves. You need air for the sound waves. What if and Einstein cuts off and says, Mahesh, any wave you take, it requires a medium. And so Einstein says, whatever waves we use, even though waves don't have inertia, all waves require some or the other kind of medium. And so when you're traveling through that medium, from my perspective, that medium is traveling backwards, giving me some kind of wind. And it's the escalator effect that's causing that's making that wave to be at rest. That's causing that wave to be at rest. Not because I am moving, I am still at rest, which means you can't even use waves to detect motion because all waves require some kind of a medium. But Einstein, you put an asterisk over here. Why is that? Oh, because light does not require a medium. Is that what makes light special? And Einstein says, yes, let's not jump to it. But the conclusion over here, the summary so far is that particles have inertia, so you can't use that to detect motion. Waves, almost all waves except for light, require a medium, and therefore they will have the escalator effect, and because of that you can't detect motion. And since any experiment that you do would either involve particles or waves or a combination of them, there is no experiment you can do to detect constant velocity motion. So the only logical conclusion of this part is that whatever Einstein said earlier, that it's him that is at rest and the rest of the world and I am moving towards him, it's a perfectly valid viewpoint. It's not just an illusion. It's not that Einstein appears that his car is at rest. No, his car is at rest. It's a fact. It's as valid as me standing on the ground saying that I am at rest and car is moving. Motion is relative. This is what we call Newtonian relativity, which basically says that constant velocity motion cannot be detected. That's how our universe works. Until we discovered that light is an electromagnetic wave. See, for a long time, we thought light was a wave very similar to sound. It traveled through some kind of a medium. We believed that medium, we called it the ether medium, and we believed that medium existed throughout the universe. But fast forward to 1900s, because of James Clerk Maxwell and Faraday and a bunch of other folks, we realized that light is an electromagnetic wave. What's the specialty of electromagnetic waves? They don't need a medium. Electromagnetic waves can travel through space. At this point, Einstein asks us, Mahesh, do you understand the implication of this? And I say, yes. Yes, the whole reason why we couldn't use waves to detect motion was because of the medium. It was giving you a wind and it was using the escalator effect. But light, if it doesn't travel through a medium, we can now that thought experiment makes sense. So let's do that. So this time, Einstein, your car is traveling at the speed of light and you're gonna switch on the flashlight. We know that light is gonna come out at that same speed, the speed of light c. It doesn't depend upon your motion. But what do you see from your perspective? From your perspective, light appears frozen. And now Einstein doesn't have any way to explain that. He can't say there's a wind because there is no medium. That's what makes light special, and therefore, now Einstein, you have no choice but to accept that you are the one that's traveling through space. Which means the fact that light does not require a medium somehow breaks relativity. And Einstein says it's not just going at the speed of light. Even if you were traveling slower than the speed of light and you switched on the flashlight, then we would see light going ahead of us, but much more slowly than the speed that Maxwell predicted. And so we would be able to detect any velocity motion. And therefore, if light does not travel through any medium, it travels through space, we don't get an escalator effect, and therefore we can detect motion. And so what does it mean? So light breaks Newtonian relativity. How do we solve for this? Einstein, what happens next? Well, Einstein says most folks, our first instinct was to think that Maxwell screwed up somewhere. I mean, this can't be true. So a lot of us thought that no, light cannot travel through space because of this problem. Light must be traveling through that medium. Ether medium must definitely exist. In fact, people believed in ether medium so much that we thought, let's do an experiment for it. See, Earth is traveling through space, and therefore, just like with the case of Einstein in the car, if we shine light in the direction of Earth's motion, it should travel slightly. We should detect it to be slightly slower than the actual speed of light. And that way we could find the speed of the ether and the speed of Earth's motion and all of that. But when we did this experiment, in fact, Michelson and Morley tried to do this experiment, and when they did that, we found the speed of light to be exactly c, 300,000 kilometers per second, whatever was predicted by Maxwell. We didn't find any difference. In whichever direction we measured, we always found the speed of light to be exactly the same. What did it all mean? Einstein says this and other experiment shows that there's nothing wrong with electromagnetism. Maxwell was good. So there's nothing wrong with electromagnetism, and we believe in Newtonian relativity. That cannot be broken. So there's only one way to put this all together. If light does indeed travel at the speed of light, and constant velocity motion should be undetectable, there's only one logical conclusion. The speed of light should be the same for all observers, even the ones traveling close to the speed of light. That's how Einstein came up with this postulate. Does it make sense now? Can you see the motivation behind it? The very reason he had to do this, because it was the only logical conclusion. Because that's the only way constant velocity motion can be undetectable and light can still travel in vacuum. Isn't that amazing? But I say, Einstein, that's just not possible. How can that be true? For example, if let's say the speed of light to be 100 for simple numbers, 100 units per second, and we have a spaceship that's going at 90 units per second in the same direction. If I wait for 1 second in my clock, that light would have traveled 100 units, the spaceship would have traveled 90 units, but look, from the spaceship's perspective, that light has only gone ahead of the spaceship by 10 units in 1 second. And so when people inside the spaceship try to measure the speed of light from their perspective, they will find distance by time equals 10 divided by 1. They will see the speed of light to be 10, not 100. Your postulate cannot be true, Einstein. And Einstein says, Mahesh, I had the exact same thought, but with one difference. I had a slightly different attitude. You see, he says, I am being extremely close-minded over here and saying that it's impossible, versus Einstein was asking himself, what should change in his thinking to make that possible? And I asked Einstein, explain to me. What do you mean exactly? So Einstein says, this is correct. This is from Newtonian physics. This is what we get. But from my postulate, I want this number to be 100. I want even this observer to see the speed of light to be 100 units per second. So I started thinking, how can this be true? How can I make this happen? And well, what's the only way to make this happen? Well, I need to find a way to make this number higher. What is the only way to make this number higher? Well, it's a fraction. The only way to make that number higher is to either reduce the denominator or increase the numerator. And I said, well, what do you mean reduce denominator, increase numerator? What are you talking about? Einstein says, think about it. If the denominator has to be smaller, then that means the time measurement should be less than 1 second. But how can that be? How can they measure time less than 1 second when we already know 1 second has passed? What if when 1 second has passed in our clocks, 1 second has not yet passed in the clock in the spaceship? Then the time over here that they measure, that they put in over here, would be less than 1 second. And since they are not allowed to detect any discrepancy in their time, because then they would know that they're moving, that means not only have their clocks slowed down, that means their entire time must have slowed down. Time dilation. That's how you discover time dilation. And I'm like, wait a second. You're saying the idea of time dilation, which completely revolutionized physics and made you the most famous scientist in the history of mankind, that discovery came by your idea of trying to reduce the numerator and increase the denominator? That's where it comes from. And Einstein says, well, that's a bit of an oversimplification, but kind of, yes. The whole idea was to try and keep the speed of light the same for all observers. That's where it comes from, folks. This is it. This is how the time dilation was discovered. Of course, it's a bit of an oversimplification, but this is it. Wow. Anyways, I asked Einstein, well, what about the numerator? How can they measure distance more than 10? I see it right over here that distance is 10. And Einstein says, well, the only way they can measure the distance to be more than 10 is if somehow their ruler size is not the same as our ruler size. What if somehow their ruler size shrunk? Then the unit shrinks and they will have to count more units between themselves and that photon, giving you a higher value for distance, length contraction. So just from the idea of keeping the speed of light a constant, we discovered length contraction, time dilation. And Einstein says, of course, there are some other effects that we need to consider, but if we do that, then we can see that they will indeed see the speed of light to be exactly the same, c. If you put it all together, let's summarize. How did we do it? How did we discover relativity? We start with the fact that constant velocity motion cannot be detected. You can't use particles because they have inertia, and you can't use traditional waves because they travel through a medium, and that gives you a wind, giving you that escalator effect. However, light does not require a medium to travel through it. It can travel through vacuum, and so you can use light to detect motion, constant velocity motion. But since that's forbidden, there's only one possible logical outcome. The speed of light must be the same in all frames of reference. All observers must see the same speed of light. But how can that happen? The only way that can happen so that all others can see the same speed of light is if we abandon the notion that time and length are same for everyone. If we agree, if we accept that time and length can be different from different people, we can cook up it in such a way that all observers can see the same speed of light. Relativity is preserved. And so in some sense, relativity is not about things that is relative. It's about the only thing that is not relative, and that is the speed of light. And Einstein says this is just the tip of the iceberg, Mahesh. If we have appetite for a little bit of algebra and geometry, we can even derive the equations for time and time dilation and length contraction. We can derive new equations for energy and eventually rederive E equals mc squared. So if you really want me to do that video, I need some feedback that this video was actually helpful for you. And that one way of getting that is please subscribe if you haven't already. Do let me know that if you would like to learn more of this stuff. The whole idea is to try and make it as intuitive as possible. That's it for this video. See you.